Hello! In this video, I'm going to demonstrate how to create interactive Python applications in Jupyter Notebooks using the library ipywidgets. For our demonstration, we will need to have installed a recent version of Python and the following libraries: Jupyter, NumPy, ipywidgets, and pqplot. And a content distribution includes everything we need except for pqplot. I will leave a link below with instructions on how to install pqplot. We create a Python 3 notebook. We call this app demo, and we add additional cells to type our code. In this demo, we will create a simple window with a real-time plot, a sine wave that advances over time, a button to stop the animated plot, a progress bar that will display the current value of the sine function, and a slider that will define the noise level applied to the current sine function. We will be using several widgets from the ipywidgets project. We will start importing them now. We will use label, float progress, float slider, and button. To build our application, we will also need auxiliary objects from the ipywidgets that will help define the layout. We will use layout, horizontal box, and vertical box. We also import the display from Jupyter, IPython. We will need NumPy, pqplot, time, and threading. To control the main loop of a real-time plot, we create a Boolean flag variable. We generate x and y data to plot, x being a linearly spaced array, and y being the sine function applied to x plus 1. Next, we'll start creating the GUI Elements. Then, we create a button to stop the application. Its description will be stop. It will use the warning style and the stop icon. The layout object will define the button width. This will create a button, but it has no action configured yet. We will create a function that takes care of the desired action. We take the value of the flag object from the global scope and modify it to false. We create a progress bar and a label to display the current value of the sine function. The initial value of the progress bar is the last value of our y array. It varies from 0 to 2. The description is PV, and we change its width to 365 pixels. The style attribute is here to modify the description width according to its content. The label is initialized with the last value of our y array as well, and with some margins. Finally, we join the progress bar and the label in a box using the horizontal box. At last, we create a slider that will handle the user interaction. It will be initialized with a value of 0, indicating no noise at all, and a maximum value of 0.5. Its incremental steps will be of 0.01. Okay, now the only element that is left for us to create is the plot. The pqplot library has an API with syntax similar to matplotlib.pyplot and an internal object model API. We will focus on the latter on this project. We start creating linear scales for our horizontal and vertical axes. We create our horizontal axis with a label x of t and refer to the x linear scale created previously. The default orientation is horizontal. The vertical axis is created with a label y of t, the y linear scale created previously, and the vertical orientation. In this demo, we will only have one line plotted. The line is initialized with the x array, y array, and the scales. To finalize, we join everything in a figure. We use the ipywidgets layout object to define the figure size. We add the axes, lines, and define the margins. Then, we join the figure, the progress bar, and the slider into a box, using the vertical box and apply a solid border. Finally, we join the stop button with the previously created box using vertical box again. The final object containing all widgets is called app. Now, we will create a function that updates the real-time plot. We call this function work. We will modify the x and y arrays in the thread and in the main kernel. So we bring the object from the global scope to the local scope using the global keyword. Our function will keep running while the flag object is set to true. On each loop, the actual value from the slider is copied to a variable a. The first values from the x and y arrays are removed. An equally spaced increment is added to the x array. The noise is calculated based on the value from the slider. The new value of the y array is calculated applying the sine function to the last value of the x array plus 1 plus the noise value calculated earlier. The value of the progress bar and label are updated with the last y array value. The line object is updated with the x and y arrays. And finally, we add a sleep time to control the speed of animation. We create a thread and direct it to run the work function. We display the app created previously. And finally, we start the thread to animate the plot. We can visualize that the old values of the x and y arrays are being deleted, while new values are being added. If we change the values of the noise slider, it will be updated on the plot automatically. As expected, the progress bar and the label are tracking the last value of the y array. If we press the stop button, the animation will stop. This concludes our quick tutorial. My name is Everton Calling. Thanks for watching.